In this lesson, we will concentrate on the regulatory requirements for Class B multi-engine aeroplanes in the climb. These regulations are applicable only to the operation of multi-engine aeroplanes in the commercial transport category. The take-off climb requirements for Class B multi-engine aeroplanes are contained in JAR OPS 1. But as for the take-off requirements in the previous lesson, the climb regulations can be found in CAP 698 on page 9 of section 3. There are two main regulatory requirements which must be satisfied for multi-engine Class B aeroplanes. Firstly, the aeroplane must demonstrate that it can clear all obstacles within the take-off climb path, and secondly, that it can achieve and maintain the minimum regulatory climb gradients. We shall discuss the obstacle clearance regulation first, and for this we will use the original wording in JAR OPS 1, as opposed to the abbreviated version of the regulations in CAP 698. In JAR OPS 1, we read that an operator shall ensure that the take-off flight path of aeroplanes with 2 or more engines, determined in accordance with this subparagraph, clears all obstacles by a vertical margin of at least 50 feet. The take-off flight path that this regulation refers to begins at 50 feet above the surface and ends at a height of 1,500 feet above the surface. However, there are several conditions that must be considered when complying with the 50 feet vertical clearance requirement. The first of the compliance conditions is that the aeroplane is not to be banked before it has reached a height of 50 feet above the surface, and that thereafter the angle of bank is not to exceed 15 degrees. The second compliance is that failure of the critical engine must be assumed to occur at the point on the all-engine take-off flight path where visual reference for the purpose of avoiding obstacles is expected to be lost. Thirdly, the gradient of the take-off flight path from 50 feet to the assumed engine failure height is to be equal to the average all-engine gradient during climb and transition to the en route configuration, multiplied by a factor of 0.77. Making this correction to the gradient gives a net gradient. The fourth condition of compliance is that the gradient of the take-off flight path from the assumed point of engine failure to the end of the take-off flight path is to be equal to the one engine inoperative en route climb gradient shown in the aeroplane flight manual. Finally, the regulations require that not more than 50% of the reported headwind component, or not less than 150% of the reported tailwind component, is to be used. The best way to gain an effective understanding of these compliance rules is to work through several examples. Before we look at the compliance issues, let us examine how to calculate whether a pilot will achieve the required obstacle clearance of 50 feet. In order to calculate this, various items of information are needed. Shown on screen is an example aeroplane at the 50 feet screen height, with a representative obstacle of 750 feet above ground level and 9,000 feet away from the aeroplane. In order to calculate the vertical distance the aeroplane will gain and therefore work out the obstacle clearance, the gradient of climb achieved by the aeroplane needs to be known. This gradient can be extracted from a graph or table in the aeroplane flight manual. On screen is an example climb graph for a multi-engine Class B aeroplane. This graph can be found on page 13 of section 3 in CAP 698. Working through the graph, let us assume the temperature is 10 degrees centigrade at an airfield 8,000 feet above mean sea level and a weight of 4,750 pounds. It can be seen that the all-engine rate of climb is 1,330 feet per minute. This equates to an approximate climb gradient of 12%. This is the gross gradient. JAR OPS states in the obstacle clearance compliance rules that the all-engine gradient must be factored by 0.77 to produce the net gradient. Multiplying 12% by 0.77 produces a net climb gradient of 9.24%. The gradient should also be corrected for wind by applying 50% of any headwind component and 150% of any tailwind component. But for simplicity, here we shall assume a zero wind condition. Using a climb gradient of 9.24% would mean that the aeroplane would gain a height of 832 feet in a horizontal distance of 9,000 feet. But the aeroplane's total height above the ground will be 882 feet, because the aeroplane is already at 50 feet. In this example, the aeroplane will clear the obstacle by 132 feet, which is well above the minimum clearance of 50 feet. The example we have just discussed changes dramatically if the pilot loses visual reference with the obstacle, perhaps because of a low cloud base on climbing away after takeoff. You may recall that one of the compliance conditions requires that failure of the critical engine should occur at the point on the takeoff flight path where visual reference for the purpose of avoiding obstacles may be expected to be lost. What this means is that when the aeroplane enters cloud, the assumed performance must be based on one engine only. In our example, let us assume the cloud base is at 500 feet. The aeroplane will climb at the all-engine gradient multiplied by 0.77 until cloud base is reached as depicted on screen. However, at cloud base, the assumption is that the critical engine fails, and the gradient which must be assumed from this point is the one engine inoperative gradient. The one engine inoperative gradient can be obtained from the same graph that we used earlier. That graph is shown on screen here. The one engine rate of climb works out to be 172 feet per minute, which equates to an approximate gradient of 1.54%. Returning to the example scenario, we see that climbing with a 1.54% gradient after it has reached cloud base, the aeroplane is not able to clear the obstacle. So in this case, during the flight planning stage, the pilot may have considered reducing the mass of the aeroplane in order to increase the climb performance. However, reducing the payload will reduce the revenue for the flight, so there is another way to solve this problem of being unable to clear the obstacle vertically.